Awesome. Thank you again for inviting me for the third time. Whoops, I'm going to put this here. And as I was saying before, if you're on the Zoom and you can't see me or hear me or something, just give a shout out. And also, I want this talk to be very interactive. So please interrupt me with questions and comments and concerns and whatever. Feel free to redirect the talk if you would like to. So as I suggested, and this is joint work with Vivek Shenda, sort of a program to prove homological mirror symmetry. That's what HMS stands for. So I'm beginning my talk with a brief review of what's this homological mirror symmetry thing, a very brief review. It says that for X a Kähler manifold, there should be a dual Kähler manifold. X check. Maybe these aren't Kähler manifolds. Maybe there's like slightly more general class of spaces, like maybe X is a sort of Liouville sector, as I'll discuss, or Weinstein. I mean, I should say Kähler manifold, like it's a Stein manifold. Stein, Weinstein, pretty much the same thing, as we know. So maybe X is like a Stein sector in the sense of Gammage and Shenda. Anyway, roughly speaking, homological mirror symmetry says that for X a Kähler manifold, there should be a dual Kähler manifold such that the symplectic geometry of X, as encapsulated by its Fukaya category of Lagrangian submanifolds, with categorical structure coming from counts of pseudo-holomorphic disks, should be equal to the category of coherent sheaves of the dual Kähler manifold X check. So this is the goal, is to understand how to prove this. And the strategy for proving this, this is if you're a mirror symmetry person, this is your goal in life of homological mirror symmetry, is to prove some equivalence of categories like this in the most generality you can. And so how are we going to do this? So our strategy consists of two parts. And those are going to be the two parts of the talk. So the first part of the strategy and the first part of the talk is what you should do is kind of, well, so you're going to degenerate both of these varieties in a certain prescribed way. So for instance, the category of coherent sheaves on a general algebraic variety could be very complicated. But what I can do is I can degenerate X check to a variety, to a singular variety whose components are simpler. So the example that you should keep in mind is if X check is an elliptic curve, an elliptic curve is sort of a complicated algebraic variety. And much simpler than an elliptic curve is P1, right? So imagine that I take this elliptic curve and I degenerate it by sort of crushing some circles here into nodes. So I get sort of 3 P1s meeting nodally, the 3 bananas. So now this category, which was complicated, is replaced by the study of this category, which is simpler. And the reason it's simpler is that coherent sheaves on this limit variety, maybe I should give this a name. Let me call this singular variety X check LCS. That stands for large complex structure. I'm imagining that this is happening in some limit where I'm making the sort of complex structure very large. I'm going to a limit in the algebraic moduli space of this variety. And coherent sheaves on this variety can be glued together. The category of coherent sheaves on this variety can be glued together from the categories of coherent sheaves on the components of this variety. Good question. No, I don't. So yeah, at the start, right. So what's the data that I'm starting with? I mean, let me say that, yeah, even formulating this, what are these pairs, is like really hard. So at the beginning, maybe I'm saying that this is some sort of general program that I would like to do, but I don't know how to do this. So let me, yes, let me return to that question in 1 second once I say what happens to X. So, and then I'll say that kind of this, from this, I reach an easier statement at kind of large, at this limit point. And then maybe I'll just say out loud in answer to your question. The strategy has two parts. One is prove some version of this equivalence at this limit where I've taken very degenerate versions of both of these spaces. And step two is to figure out how to kind of go from this limit point back to like a more general case. So I'll explain more about that in a second. But so this first part of the strategy, what we're doing is we're degenerating X check to this singular variety. And what that corresponds to on X is that the symplectic form on X inflates along some divisor D. And what happens is that kind of as we inflate the symplectic form more and more along this divisor, like any holomorphic curve passing through this divisor gets bigger and bigger area until it gets kind of infinite area. And so no, we're not allowing any curves to pass through that divisor. So in other words, what we're doing is kind of we're replacing the study of the Fukaya category of X with what's called the large volume limit space of X, which is X minus this divisor. So once again, the Fukaya category of this space is a lot simpler than the Fukaya category of X. And the reason is that holomorphic curves, we've thrown out all the holomorphic curves that can pass through X. Throw out J curves, sorry, through D. We've thrown out all the holomorphic curves that can pass through that divisor D. So that simplifies the situation a lot. So let me okay, maybe I can kind of state a theorem here. And this is kind of the first kind of theorem of this talk, which I'm going to make precise later. But this is in a paper of mine with Vivek Shunda. What we prove is that kind of we can construct, given some combinatorial data, which I'll tell you about later in the talk, we can construct these pair of spaces, the large volume limit space and the large complex structure limit space, and we can prove this equivalence between those spaces. And maybe I should give a little example here that's going to be the dual to this example here. So the example of X LVL in this case is that if I start with an elliptic curve, maybe what happens is that I delete a few points from this elliptic curve. So I puncture this elliptic curve in 3 points. So puncturing this elliptic curve in 3 points is dual to kind of pinching the mirror elliptic curve in 3 points. And so this is one of the simple cases of our theorem, is that kind of the Fukaya category of this thing is the same as coherent sheaves on this thing. But this isn't really the theorem. The content of our theorem is sort of in explaining how to construct these spaces from, how to construct this space from some combinatorial data, which I'll describe you. In fact, content of the theorem is in a construction of this large volume limit space. And then to answer the previous question, let me say, so this was all part one of the strategy, and part two of the strategy. It's a wrapped, here it's a wrapped Fukaya category. Or if this is a sector, then it's a partially wrapped Fukaya category. I'll say any dimension. Yeah. I'll be a little more clear about what this space is. This space is I'm going to give a very concrete construction of this large volume limit space soon. Ultimately, I will say that like what we're going to do is that when I try and move, well, let me hold my remark for just 1 second. Let me say part two. So part two of the strategy is going to be given this equivalence star. Given star, compactify this. So this thing right now is a Weinstein manifold, and we'd like to compactify it to a compact symplectic manifold X. And this space right now is a singular algebraic variety, so we'd like to smooth it to a smooth manifold X check, and then prove that coherent sheaves on this sort of X check is equal to the Fukaya category of X. So step two is going to be kind of, and this equivalence, let me call this star star. And this equivalence here will be a deformation of the equivalence star. So what I mean by a deformation is that, well, I'm kind of deforming both of these categories, right? On the right-hand side, I'm like deforming this. I have a singular variety here, and I'm sort of smoothing it out so it fits into a family where this is the central fiber and this is the general fiber. So I have sort of a family of categories going from this singular category to this smooth category. And likewise over here, I have a family of categories as I sort of give, as I blow up my symplectic form, as I give sort of more and more symplectic area to these 3 points until in the limit they become, it gets inflated to infinity and they drop out. So, okay, so that's my sort of brief overview of the talk. So now I'd better, any more questions? Oh yeah, sorry. I was going to answer Kyler's question again by saying that I have coherent sheaves. The Fukaya category. The spaces, these symplectic manifolds here, I'm always going to want them. They're going to have Lagrangian torus vibrations. Basically, that's the structure which we're going to use a lot in this talk. But they can be any dimension. Sorry, Julian.
So is there like a nice way of geometrically seeing why the mirror should, why like this kind of degeneration along a divisor corresponds to this like this kind of
yes. So I'll move. I'm going to move over here for this question. The answer is that kind of mirror symmetry is about dualizing a torus vibration, right? So if I think about what the torus vibration is on this thing. I can see that kind of what's happening here. So this has a torus vibration down to the circle, right? These are the kind of torus fibers here, right? And what's happening is that near a few points on the circle, these torus fibers are getting pinched to 0, right? The circle is getting smaller and smaller till it gets 0 radius. So when I dualize these circles, they should be getting bigger and bigger until they get to infinite radius. And what's an infinite radius circle? It's like a line, right? It's like a circle where I've deleted a point from it. So you should think that kind of the dual to this is that kind of over these, wherever they are, over these 3 points where I've pinched something on the kind of dual thing, this circle has gotten infinitely big, and so it's like lost this point at infinity there. That's your geometric intuition for why these two things are dual to each other. Did that make sense?
Yeah.
So we're going to make more sense of that now, and I'm going to explain the combinatorial data that is kind of interpolating between these and what the construction is. So okay, we're back to 1. And in order to figure out what this symplectic manifold is, XLVL, what this symplectic manifold is, wherever he went, we should take inspiration by looking at this algebraic variety X-check LCS. So in good cases, so I said that we want to sort of degenerate this to something singular whose components we understand. And also, they should be meeting each other in a very prescribed way. And so the best case is that this variety is a union of toric varieties, and they're glued along their toric strata in a normal crossings way. So in good cases, X-check LCS is toric normal crossings. So these are toric varieties glued together along their toric strata. So the question which we can ask ourselves is kind of what's the, how to describe, question, how to describe this space combinatorially. And the answer is a sort of combinatorial topological model that Vivek Chanda and I call a fanifold, which is obtained by gluing together the fans of these toric varieties. So the answer I'll say, and now I'll explain what I mean, is glue together fans of these toric varieties into a fanifold. So what is this fanifold, and what do I mean by gluing together the fans of these toric varieties? So the example, yeah, normal crossings means like, I mean, maybe simple normal crossings is what I would really like, which means locally looks like x0 dot 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 xn is equal to 0. So this like locally near this point, this is the simplest example of a normal crossings divisor, right? It's a node. It looks like xy equals 0. And kind of the next, the next example up would be like, xyz equals 0, which would look like, 3. Here's like a moment polytope picture of kind of what's happening there. But I'm actually going to be interested in the fan pictures for now. So let me consider.
Of those variables, x0 to xn in the same dimension.
There's some number of variables here. Let me say x0 dot 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 xk equals 0. It can be a product with some. Those are not necessarily all the variables. Yeah, so these are like some of the variables look like this, and the other variables can do whatever. Can be smooth. So the example I'd like to consider is kind of glue together two P2s along a P1, right? So the moment polytope picture, which I'm going to return to later in part 2 of the talk. So just to give a little roadmap where I'm going, part 2 of the talk will be about moment polytopes, and part 1 will be about fans, which are dual to moment polytopes. So, but let me just draw the moment polytope picture. So I have a P2, and then I have another P2, and I identify them along this P1 here. So I'm taking these two P2s and I'm gluing them together. So hopefully that little picture makes sense here. This is a P2, P2, and I've got a P1 in here. And the fan picture is that I have the fan of P2. Sorry, let me move up here for my fan picture. Oh, this is a good eraser. The fan picture, I have a fan is dual to the moment polytope. Fan of P2. I have another fan of P2. And what I'm gluing them along is that, so let me call this sigma 1, and let me call this sigma 2. And then I see that this P1 that I'm gluing them along corresponds to a ray inside these guys, right? So let me call this sigma 1, little sigma 1, and this little sigma 2 is this ray here that I have here. And so the fan of the P1 that we glue along is, if you know your toric geometry, or if you stare at this picture, it's the quotient fan. Right, a ray corresponds to a toric divisor, and the fan of that toric divisor is the quotient fan of this fan modulo this fan. And what I'm doing is I'm saying that the fact that I'm identifying the P1 to glue them in these two copies of P2 says that I'm identifying these two fans here. Oh, so right. So given a toric variety, there's two ways to depict it combinatorially. One is the moment polytope, which, as we know, is the image of the moment map of the natural torus action on the toric variety. The other is the fan picture, which Well, one way to think about what the fan picture is that it's telling you the it's telling you directions. So this is the fan. These are living in the space of co-characters of the torus that acts of the torus. So right, the moment polytope picture is happening inside the space of characters of the torus, because it's, the moment image is the dual of the group, or dual of the Lie algebra. And this is living in the space of co-characters, so it's dual to the moment polytope. You can take as one description of the fan that maybe the simplest thing I should say is just that you can think of it as the normal fan to the polytope if you have a polytope. So kind of all the normal directions pointing out give you a fan of cones, and it's this fan here. The other thing I could say is that kind of the directions in the fan indicate the different possible limit points that you can go to. Cones in the fan indicate limits of the torus action. So on P2, if I think about it like if I take a general point with coordinates, say like sorry, if I go along this way, then I'm going to end up in the point 0, 0, 1. I mean, so these things correspond to the points like 0, 0, 1, and this guy corresponds to like 0, 1, 0 or something, and this guy corresponds to the sort of P1 0 A B. Sorry, maybe that's not the best explanation of fans, but for now you can just think of a fan as if you're not used to fans, you can think of it as dual to the moment polytope. And so this is what a fanifold is. This is this new structure which we're introducing. And what it is you glue fans together in this way. So glue together fans along quotients, yes, along quotients. So right, this is a fan of cones, and sort of if I want to glue together the fans sort of along here, then what I should do is I should kind of take the quotient by sigma 1 and the quotient by sigma 2 and identify them that way. So in other words, what I'm doing is that this, the result of this construction is sort of a stratified space where kind of along each where each stratum has a fan of normal directions. Right. So if I identify these two, fans along the quotient by sigma 1 and sigma 2, that means sort of along this shared ray here, I've kind of forgotten about what's happening to those tangent directions, right? I've quotiented out those tangent directions, but I still have this sort of remaining part of the fan that's in the normal directions to here. So if I kind of glue together these things, then this is kind of what you end up with. You end up with kind of this, so in this case, when I glue them together, I have a space that looks like this, right? I've kind of glued together the fans, and now kind of the way it works is kind of along each ray, I have a fan kind of normal to the ray. Like I have a fan kind of normal to this guy, but I don't have a fan of cones along this guy. And at the vertex, I have a full fan of cones. So kind of at each vertex, I have a full fan of cones, and I've identified them in some way. So this is the combinatorial structure, which I would like to use to build a Weinstein manifold. So for everyone who zoned out for a while because I was talking about algebraic geometry, you can come back in. I'm going to build a Weinstein manifold now. So near each vertex, I have a fan of cones, right? In this picture, like each vertex, I have this fan of cones near it.
So that's a representation of the Fanifold, right?
Yes. It's dual to the polytope picture, right? So this picture here, you can see is dual to this picture here. So again, but so, sort of the point is that I like the Fanifold better because not every toric variety is quasi-projective. Not every toric variety has a notion of moment polytope, right? I can't necessarily polarize a toric variety. So the fan picture is more general.
And this thing that's associated with this vortex is the fan to quotient fan.
No, well, the vertex has the full fan and the edge has the quotient fan by the tangent vectors. And like the reason why this edge comes equipped with a normal fan is because if I take the normal vectors to this thing, if I take the normal vectors, that's like that's exactly the same as quotienting out that tangent direction, right?
The other edges doesn't mean anything. It's just a picture for
Well, they also have quotient fans, so I could use them to glue more fanifolds to them or something. So, okay, now I'm going to show you how to build a Weinstein manifold.
Say it is built by polarizable toric varieties. What's the definition from the polytope point of view? It's just gigabytes of polytope and identify faces and entropy.
Yeah, so each polytope has a normal fan.
But without fans, you just say it's polytope.
Well, I mean, it's dual to the polytope picture.
Yeah, but is it just a collection of polytopes when you've identified?
Well, it's dual to that.
Just like in the case where it's actually built out by.
Yeah, in the case where it's built out, like suppose I have these two P1s and I glue them together, then what have I done? Well, the Fanifold is some polyhedral complex that's dual to that. And I notice that kind of a vertex of this Fanifold corresponds to a polytope, a top dimensional polytope. So it has a normal fan associated to it, which is the dual fan of the polytope.
So in that picture, there's no other data that have those two polytopes that you could.
Yeah, that's more data though, of course, because choosing a polytope is like choosing a polarization. So that's more data. I'm forgetting a lot of data when I switch to the fan picture.
From that data, then you could forget.
From the data of the polytopes, I can forget down to the fan picture. Yes. Sort of because I don't care about how big these polytopes are, for instance.
Manifold is more general.
Yes, the Fanifold is more general than the polytopes. This is the picture. Yes, well, every picture is going to be on both objects, and there's two dual pictures, and they're both telling you things about both objects, which I'm very sorry. That's one of the great confusions of mirror symmetry, is that there's two dual representations of the same thing, the moment polytope and the fan picture, and each one of these tells you something about each one of these spaces. But so far, I've been talking about X check. Yes, this discussion has been about if you give me like basically the thing is if you give me a Fanifold, then I can give you back X check in just this way. So maybe I should say that, lemma. There is a Cauchy of algebraic varieties over the Fanifold. In the sense that, like, given any vertex which is a fan, that's like a moment polytope, that's like a toric variety. And then given an edge, I have like something else, and I glue these toric varieties together along that edge. So when I write Cauchy, that just means that this Fanifold is a recipe for gluing together toric varieties. So maybe I should write that somewhere. That's also true. But yeah, so a Fanifold. So from the algebraic geometry perspective, a Fanifold is a recipe for gluing toric varieties along toric divisors. And kind of if you were much more restrictive, then you could say the moment polytopes do that as well for a certain class of polarized toric varieties and blah, blah, blah. But the Fanifold tells you how to do it for all toric varieties. And likewise, this also tells you how to glue not just the toric varieties, but also the categories of coherent sheaves. Toric varieties and coherent sheaves on toric varieties. So what we would like to do is we would like to construct some Weinstein manifold from this Fanifold whose Fukaya category has the same kind of locality. So we would like to glue together a Weinstein manifold So goal, manifold as recipe for gluing Weinstein manifold.
Variety, like generations into toric varieties or varieties with toric components. I thought that was conjectural.
Yeah, that's why this is where I'm starting from. This is my starting point now. I've thrown out the first part of the talk. That was motivation.
And do you know what general?
Well, it depends. I mean, but you should want to go the other way. Like I'm going to start here on the large complex structure, large volume limit, and then your question is how, in what generality can I, smoothing out those things, how many spaces can I get? And there's been some work on that. There's which I'm not going to be able to say all off the top of my head. Let me say that in general, my restriction of toric normal crossings was too much. We can loosen that. There's these toroidal crossing spaces which are a little more general. But you can get quite a lot of spaces by smoothing toric varieties. There's a good paper by, there's some papers by Chan Lao Lung, I think, and is that right? There's some paper, no, Chan something Ma, and there's some papers by Rudat and his collaborators on kind of smoothing these singular spaces. Anyway, so the Fanifold, so our goal here now is to build a Fanifold, is to treat the Fanifold as a recipe for gluing together Weinstein, maybe gluing together Weinstein sectors into a Weinstein manifold. And also gluing the categories together. So the Fukaya category gluing together Weinstein sectors and their Fukaya categories. Okay, so we've gotten to the symplectic geometry portion of this talk now. So here's how the construction is going to go. Construction. Yes. 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 Closed descent so that, yes, I'm gluing together these along their kind of toric subvarieties that I'm gluing them along. That's mirror to sectorial covers of Liouville sectors. Homotopy co-limit over the. I said Kashif. But I don't want to get into these technicalities. But I did say Kashif, so I'm good. But you can always sort of pass to big categories and dualize, whatever, pass to adjoints. Yeah, that's sort of, yes. Although it's pretty straightforward. I mean, somehow like, I don't know. This is one of these, well, I don't know. I'm quite proud of the Fanifold thing, but in some respects, I know it seems obvious. happen again. Okay, the light is on now. But it's red now.
Okay, so
It's low. I'm getting a low battery sign
Yeah,
here.
I'll go look for batteries. No, let me go get batteries. Then you can stay. You're the resident nurse.
Okay, they can hear us now. Okay, well, yeah, so it said, just as an update for people online, it said dead battery, but we took the batteries out and on again. So hopefully this will survive for a minute until Julian finds 2 more AA batteries. So let me begin trying to describe the construction of a Weinstein manifold from this Fanifold picture. So what we're going to do is so start for each vertex. So I'm going to assume my Fanifold is n dimensional now. I'm going to assume it has a dimension, which is n. So for each vertex, take a copy of, take a disjoint union of copies of the cotangent bundle of an n torus. And what we're going to do is we are going to glue these together. We would like to attach handles, gluing these together. So let me give a little, just a heuristic picture for those of you who are familiar with skeleta of Weinstein manifolds. So suppose my Fanifold looks like this, say. So right, this is a Fanifold which I would get if I took 3 copies of a fan that looked like this. So maybe let me draw it up here. So if I take 1 copy of the fan of C2, and I take another copy of the fan of C2, and I take a 3rd copy of the fan of C2, and I glue them all together like this. So this thing is dual to dual to this picture here. So if I have this Fanifold, then then in the end, what I'm going to produce is I'm going to produce a Weinstein manifold with skeleton that looks like this. It's going to have 3 2 tori, 1 for each of the vertices here. And they're going to be connected by cylinders, 1 for each of these edges here. And there's going to be a 2-cell, there's going to be a Lagrangian disk in the middle, which runs along these sort of pieces of cylinders here. So this is going to be the Weinstein manifold, which I associate to this thing. So let me kind of zoom in now on a vertex and kind of say what's happening here. There we go. All right, it's green now, so that's good. It's got full battery. Hooray. Yeah. And then, of course, for this cone in the fan, I see that its perpendicular is just the point 0, but it's telling me that I want to have like a lot of the conormal to 0 as part of my Legendrian. So kind of if I draw the picture here of the Legendrian cone, of the cone on this Lagrangian. What? Okay. Well, you can let me know if people can't hear me. I've got a green light here, so I think I should be good. Right, so if I draw a picture of what this looks like in a neighborhood of this 2 torus, I have my 2 torus. And then I have, I've got my kind of red circle and my blue circle and my green circle, which, wraps around once, whatever. And I've got these cylinders coming off of it, in the appropriate ways, which are the cones on these Legendrians. And then I have the extra stuff, which comes from this thing. And I have, and so this is the skeleton of a Liouville sector. This is a sectorial structure on the cotangent bundle of the 2 torus with boundary Legendrian is this thing here. So the boundary Legendrian I can see has a red circle, a green circle, and a blue circle, and they're connected up by some 1 cells like this. And so the idea is what I want to do is kind of, I've got these kind of Liouville sectors now near each of these vertices, and I want to glue them together. And I do that by attaching handles. So let me go back to my example here. What? Yeah, so in the picture in this fan, you can see that I have these big cones in the fan, which are the 2-dimensional cones in the fan. So the perpendicular, I said, and to each like cone in the fan, you assign its perpendicular in the torus. So the perpendicular of a top dimensional thing is just like the point 0. And then the rays in this cone are all kind of conormal directions there. So at infinity, I'm giving you like some conormal directions to 0. And in fact, since these go all the way around, I'm giving you the full conormal to 0. So all of the conormal directions. So kind of this white circle is the conormal to 0 inside of the 2 torus. Or the cosphere, whatever. Yeah, the conormal directions to 0 inside the 2 torus. Does that make sense? So let me kind of draw my schematic picture again. So given this Fanifold, what I did was I started with kind of near the vertex. I had one of these 2 tori with these cylinders coming off of him like this. And near this vertex, I had some of this. Near this vertex, I had something like this. And then what I'm going to do is attach 1 handle. So in order to build this Fanifold, so this is an answer to the question, how to build this Weinstein manifold. And in order to build this Weinstein manifold, what I do is I start with these 3 guys, and then I attach handles in the appropriate way. So step 0 is start with this disjoint union of cotangent bundles of tori. And then step 1 is going to be attach 1 handles. And the 1 handles are going to be, I'm going to have a t to the attach t to the n-1 times 1 handle. So the point is that I have sort of, this is like modeling what would happen if I had a Morse spot function with a circle's worth of index 1 critical points here. So let me use colors again. Let me call this step 1 in yellow. This thing is yellow. And so what that's going to be is this is going to be like this thing here. Right, so this is kind of a circle's worth of 1 handles, which is attaching, gluing on to this thing here and this thing here. And kind of this first Lagrangian that I wrote down, which, sorry, I should have attributed this Lagrangian to first to Bondal, and then to Fong, Liu, Truman, Zaslow. And this Lagrangian tells me like what's the Legendrians along which I'm going to attach these handles. And then I see that step 2 is attach t to the n minus 2 times 2 handle. So in this case, that means I'm going to attach just a 2 handle. And what's the Legendrian along which I attach it? Well, each of these guys sort of, I wanted to glue each of these guys kind of, I want to lift this extra bit of Legendrian here, this part of the Legendrian along my handle attachment. So I really should have glued like this, like each of these yellow guys has a fin coming off of him. So kind of I'm gluing this to this via some sectorial magic. And now my orange 2-cell is I'm going to glue like a 2-cell on whose boundary is like this new Legendrian, which comes from gluing up these Legendrians here. So the boundary of my 2-cell comes from like gluing up all of these guys here like this, right? Yeah, whatever. So this is how the construction of the Weinstein manifold from the large volume limit goes. So you can see it's totally explicit. It's just about kind of starting with cotangent bundles to tori and attaching some handles to attaching some tori times handles in some prescribed way that's like totally controlled by the combinatorics. Okay, so let me pause here for questions, and then I'll proceed to what I can get of part 2 of my talk, which is just a little glimpse of what happens when you try and compactify. Mm-hmm.
So you have this construction, skeleton, some boundary Legendrian, and you're doing what?
This is a cotangent bundle of a 2 torus, right? That's what this picture represents, and this is a cotangent bundle of a 2 torus. And I'm attaching, and I take this symplectic manifold, which is a disjoint union of these 2 cotangent bundles of 2 tori, and I attach a handle to it. And to attach a handle, this yellow handle, I have to have a Legendrian that I attach it to, and I attach it to this Legendrian, which is the S1 times the boundary of a 1 disk here.
But that's only part of the sigma.
Yes. So I'm attaching because I can only attach handles like 1 step at a time. So you should imagine, maybe a better way to imagine this is that this Weinstein manifold has a Weinstein structure, which is the result of a Morse function, which has, imagine Morse function with index K critical manifold T to the n minus K at, did I do this right? Yes, at a K face of the Fanifold. So I'm imagining some sort kind of space which has index, which has a T to the 2. So in this case, it has a T2 of minima, right? T2 of index 0 critical points at each vertex. And then for each edge, maybe I should say at the center of, maybe in a K face. So it has a T2 of critical points at each vertex. And then it has an index 1 critical circle at each of these places. And then it has an index 2 critical point right here. Whoa. Does that make sense? So kind of the recipe I'm describing here is just the recipe you would do if you did Morse theory that had a Morse function that looked like that. So I start building up my manifold by saying I have these 3 guys here, and then I see that I have some flows which are connecting them up from these circles, and then I see that this index 2 thing is contributing me like a bigger flow here. So this is just like a fully Weinstein handle attachment description of what it would look like if you had a Morse function that looked like that, Morse bot function. I keep saying Morse, but I mean Morse bot. Well, now I'm close to time. Do I get extra minutes because I started late, or should I just end the talk here? 10 minutes. Well, I don't want to keep people too long, but okay. I'll just give a brief glimpse of part two, which is this deformation question. So the dual of a Fanifold. Now we're going to the moment polytope picture. So the dual of a Fanifold is an SYZ base. So SYZ to me just means these are three letters which stands for Lagrangian torus fibration. I mean, I know lots of people study like metric SYZ and hard questions like that. I'm just saying we're going to imagine that like the dual of a Fanifold is kind of an SYZ base. So let me just do this one example here. So example. So if my Fanifold looks like this, then my SYZ base looks like R2 with kind of this dual structure here, which is this red thing, right? The red thing is kind of dual to this Fanifold here. And this red thing, as you may know, what you should imagine this picture, imagine this is the image under the moment map, which is also known as taking log norm of the coordinates of C star squared. And inside C star squared, I have a hypersurface which really has an amoeba, but like it has a tropicalization. This red thing is supposed to indicate the sort of tropicalization of some hypersurface H, which in this case is a pair of pants. X plus y plus 1 equals 0. So in fact, what's happened here is that this Stein manifold, or Weinstein manifold, however you like to say it, is C star squared minus this hypersurface H. X plus y plus 1 equals 0. So this kind of is a divisor complement of the sort I've mentioned at the start of my talk. But right now, sort of the Fanifold, remember, didn't have the Fanifold had like some kind of structure, this kind of integral affine structure near a vertex. No, sorry. Oh yeah, near a vertex, which the vertices of the Fanifold correspond to the chambers over here, right? They correspond to the chambers where this red thing isn't. And along the red thing, those are the places where I was kind of in the interior of my Fanifold, where I didn't have a full integral affine structure. So what I would like to say very briefly, this is going to be my last thing I say. See, I want to move that down. Oh, well. Oh, no, my phone is ringing. Oh, well, answer it later. No, there's no singularities of the integral affine structure. Sorry, I don't have an integral affine structure yet. I have an integral affine structure. I have IAS away from the red lines. And on a red thing, on the red, I have integral affine structure only in the, before I had normal directions, now I have tangent directions, only in the tangent directions. Tangent directions. Does that make sense? Because on the Fanifold, I had integral affine structure only in the normal directions to each stratum, and the strata are dual to strata of the red thing. So kind of this tangent direction in the red stratum, like this direction here, is where I've glued together these two edges of my Fanifold here. So what I would like to say at the end of my talk is that equipping this like red picture here, this SYZ base with an integral affine structure tells me how to glue back in my divisor. My divisor H, which I deleted. So this H here is the analog of the divisor D from the start of the talk. Maybe I should have called it D. It tells me how to glue in my divisor D, which if you remember at the start of the talk, that was our whole goal, was to start from a mirror symmetry equivalence here and then figure out how to compactify, or partially compactify in this case, to glue in the divisor D. But maybe the integral affine structure has singularities. So it's possible that when I try and write down an integral affine structure, I end up putting some singularities in when I kind of try and fill in the missing parts of the integral affine structure. And that will indicate normal crossing singularities of the divisor. So if I have this red guy here, which correspond, and then I put an integral affine singularity here, this corresponds to divisor D, which is something that looks like xy equals 0. So on that enigmatic note, I'll end my talk because I'm 5 minutes over now. Sorry, I know this last bit was kind of incomprehensible, but it was just to give you a taste of what's next. Yes. Well, so in the case I'm interested in the Fanifold case, I kind of really have told you everything. This large volume limit manifold always has a skeleton, which is just glued together like this. I have these tori, and it's glued together along subtori in this way. So kind of that's kind of the whole game here, is that mirror symmetry is about tori, and mirror symmetry is about Weinstein manifolds that are kind of built out of tori in some way. Let me add just one more remark. So kind of at the large volume limit, you only ever see attachments like this from fans, Legendrians, whatever, that like I totally understand. Let me add one more remark. So kind of, if you're only interested in large volume limits, this is the only ingredient you ever need in life as a Weinstein geometer, is this kind of gluing. If you also care about things that are about integral affine manifolds that have singularities, but are still like Stein manifolds, still Weinstein manifolds that you can produce by gluing, then kind of the part of the talk I didn't get to might have told you that there's one more ingredient you have to know, which is there's another kind of attachment you do where you attach a piece that kind of takes a K-torus and collapses it down to a point. Like you take, you glue on a piece whose skeleton looks like the cone on a K-torus. So that's the other ingredient that occurs. It doesn't occur in this large volume limit setting, but it occurs if you want to study cluster varieties, for instance. But the point of this talk is that this large volume limit setting, the Weinstein manifolds are so nice. I know everything about them.
Last part, are you saying like precise symplectic form on this compactified manifold?
Oh, precise. I'm not a precise guy.
Like for example, this example you gave at the very beginning with like a three-function torus, like is there some data you can write down on this manifold?
So basically, here's how the strategy is going to go in this part, is that if you give me a symplectic manifold, if you give me an integral affine structure with singularities, I'm going to require that each of those singularities is of a sort of prescribed generic type. There's this Gross-Siebert gave us like a class of like generic singularities to consider on one of these integral affine structures. And my claim is that near each one of those singularities, I have a local model for what the torus vibration looks like. And what I'm going to do is I'm going to construct a compact symplectic manifold by gluing together all of those local models.
I guess the question is that there should be a whole sort of modular space.
Yeah, so. That's a good question. That's a good question. Yeah, well, so there's additional, so Gross and Siebert usually consider integral affine structure with polyhedral decomposition and this kind of piecewise linear function on this SYZ manifold, which the piecewise linear function is like some sort of combinatorial version of the Kähler potential, basically. So that should kind of be the data That should be some data which recovers that. I haven't thought so much about that. Let me say my answer is I don't know, but that's a good thing to think about.
Any other questions?
As you promised at the very beginning, just from the construction and the Cauchy property of coherent side and both Weinstein side to get the mirror symmetry.
Yes, yes. I never stated that, but if I have this Liouville sector, the Fukaya category, where's my Hagoromo? The Fukaya category of this Liouville sector, Fukaya category of this thing is equal to coherent sheaves on the toric variety with fan sigma. This was first proved by, you might say, by Tatsuki Kuwagaki. Well, it was first studied extensively by these guys. It was proved by Tatsuki Kuwagaki first, and then there's later proofs. There's a proof by Peng Xiao. There's a proof by Vivek. There's several proofs of this equivalence now. And then kind of here, I'm just gluing together those equivalences, just like I'm gluing together the coherent sheaves on the toric varieties. And the fact that I can glue together the Fukaya category along a Lagrangian skeleton is, of course, due to Ganatra, Pardon, and Shenda in their series of papers establishing co-sheafiness.
So anything about it also uses this GPS, right?
He proved something about, well, he proved something about sheaves. Yeah, so Tatsuki proves something. I mean, all of these guys here are proving something about sheaves, microlocal sheaf category, which is equivalent to the Fukaya category of this thing by GPS.